In this module, we will introduce the root locus technique. In this module, we will first begin by reviewing the transient response characteristics of a dynamic system, and in particular how poles affect that transient response and how we design controllers to achieve a desired transient response. We will then introduce a new graphical technique for designing controllers or designing systems in general. We will also introduce an approximate procedure for drawing the root locus, and we will try and give some intuition as to where this procedure comes from. So previously, when we began to design controllers, we basically used an algebraic approach for choosing our gains. When we have a system that has a known simple form, for example, has the form of a canonical first-order system or a canonical second-order system, we can basically use algebraic relationships to choose various parameters to achieve desired pole locations and transient performance. For example, for a first-order system, we precisely know what the effect of tau is on a system's response. And so if we can relate tau to a control gain, then we can solve for tau. Similarly, with zeta and omega n, we have exact relationships for how the parameters of a canonical second-order system affect things like overshoot or settling time. And so by matching our closed-loop transfer function to this standard form, we can choose our gains to achieve certain desired characteristics. When we have a higher order system, that is a third, fourth, fifth order system that doesn't have these simple canonical forms, then it's much more difficult to design the controller. We don't have precise relationships that we've derived for capturing the speed or the overshoot of a system. We don't even have something like a quadratic formula for precisely expressing the poles in terms of our controller gains. And so it turns out that there's a technique called the root locus that can help us when dealing with these higher order systems. So the root locus is basically a graphical tool that shows how the closed loop poles of a transfer function move as a parameter, which is usually a control gain, is varied. And so here's the complex plane, and this picture is a root locus. And these red lines show all of the locations of the closed loop poles of a given transfer function. For example, we could imagine if k equals 0, so this is maybe a proportional control gain. The location of one of our closed loop poles is located at the origin. And as we increase k, that closed loop pole moves. So when k equals 1, maybe it has that location. When k equals 2, maybe it has that location, and so on. As we increase k, we can see how this pole of the closed loop transfer function moves. In this case, we basically have 4 branches of a root locus. We have 4 lines. So this is one line, this is one line, this is a line, and this is a line. And so each of those lines shows how a different closed loop pole moves. In this case, we have a fourth order system. So this is something that would be very difficult to address algebraically, but by using the root locus, we can see how all 4 of the poles move as we vary this parameter k. And by knowing where the poles are, we can figure out which poles are dominant. We can figure out are they indicating that the response is getting faster? So moving the poles to the left in the complex plane corresponds to making sigma larger, which corresponds to a faster settling time. We can see what the effect is on beta or zeta to get a sense of overshoot. things like that. And so this is very helpful for higher order systems because we don't have these precise algebraic relationships. And they're also very useful for finding approximate results quickly. So we don't have to do 2 pages of algebra to select a particular gain. We can draw a picture like this in 30 seconds. Maybe it's not exactly correct, but it gives us a rough idea of how qualitatively changing our parameter affects the location of the poles and in turn affects the transient response of our system. Okay. So here we're going to start with a simple example to try and build some intuition about what the root locus is. Okay, so we have this closed loop system, negative feedback, typical of what we've seen before in the class, and we want to find the open loop transfer function, the closed loop transfer function, and the open loop poles and zeros. So this concept of an open loop transfer function isn't something that we've addressed in great detail, and this might be a little bit confusing, but when I say open loop transfer function, you can think of what we've called previously just the loop transfer function. So when we find the closed loop transfer function of a negative feedback system and we use the form forward over 1 plus loop, the loop is the open loop transfer function. So everything in that path is considered part of the open loop transfer function. It's as if we took the closed loop system and we broke the feedback signal and stretched it out. So it's as if I took this signal, broke it away from the summing junction and spread it out. That's the open loop transfer function. So in this case, the open loop transfer function consists of this gain proportional controller Kp, this plant transfer function, and what we have in the feedback path, which is in essence a 1. So the open loop transfer function is then just Kp times the quantity s plus 2 divided by s squared plus 2s plus 3. So that's our open loop transfer function, or our loop transfer function. And looking at this, we also want to know what the open loop zeros are and what the open loop poles are. So take a second and think about what the zeros are for this open loop transfer function. Just by inspection, we can see that we have 1, 0 at -2. That's the value of s that makes the numerator equal to 0. The poles of the transfer function we can find by applying the quadratic formula to the denominator, values of s that make it equal to 0. And so if we do that, we get that we have conjugate poles of -1 plus minus j times the square root of 2. We also want to find the closed loop transfer function, which, since we have a negative feedback system, it just has the form forward over 1 plus loop, where the forward path and the loop are exactly the same. Kp times the quantity s plus 2 divided by the quantity s squared plus 2s plus 3. So that's the forward over 1 plus loop, where the loop is the same thing. Right, so that's our closed loop transfer function. We'd like to clean it up a bit, and so in order to clear out those fractions, we multiply through by the denominator of this quantity. So we multiply through on the top and the bottom by s squared plus 2s plus 3. When we do that, it'll cancel that term, and we'll be left with Kp times the quantity s plus 2 in the numerator. And the denominator, when we multiply through by this quantity, we need to distribute it to the 1. So we get s squared plus 2s plus 3, and then when we multiply it by this term, that'll cancel. So in addition to the 2s term, we'll also have the kps term. And in terms of our constants, we'll have a 3, and then we'll also have 2 times kp. And that, therefore, is our closed-loop transfer function. And so the reason that we did that is this is going to give us some insight into what the root locus is and how we will eventually be able to draw the root locus by hand. Okay, so going to the next slide, here is where we're going to plot how the closed loop poles change with the parameter kp. So as we change the proportional gain, how do the closed loop poles move around? In order to do that, here's the open loop transfer function from the previous slide, where we found that it had a 0 of -2 and conjugate poles of -1 plus or minus the square root of 2j, and we had a closed loop transfer function of that form. So since we want to plot the closed loop poles, we're basically going to look at how the closed loop denominator changes. So we start, with k equals 0, or as k approaches 0, the closed loop denominator approaches the following. So kp 0, those go away. We're just left with s squared plus 2s plus 3. And if we look at that closed loop denominator becomes the same as the open loop denominator. Which is interesting. Okay, so if we wanted to plot the closed loop poles for k equals 0, or as k approaches 0, the closed loop poles approach the open loop poles, where we had found that the open loop poles are -1 plus root 2j and minus root 2j. Then as we change the value of k, we can see that the closed loop denominator changes. So we still have s squared. We put in 1 for k, we get 3s. Put in 1 for k, we get 3 plus 2 times 1. That's what the closed loop denominator becomes. If we apply the quadratic formula to that, we'll get a new location of the closed loop poles. And it turns out that the imaginary part increases and the real part becomes more negative. So this is what the closed loop poles were for k equals 0. This is what they were for k equals 1. And we keep doing this. So we try another value, k equals 2. We plug in, get s squared. This will be 2 plus 2, become 4s. Here, 2 times 2 becomes 4, plus 3 becomes 7. So if we find the roots of that, we get a new value for the closed loop poles. And we keep doing this, changing values of k and seeing how the closed loop poles move. If we keep increasing k, so all the way as k approaches infinity, and we plot what the closed loop poles are doing, they behave in this sort of manner. And then if we increase k enough, the system becomes overdamp. The closed loop poles go from being complex to being real. And if we look at our denominator, you can sort of imagine that as kp grows large, it will dominate this 2, As this kp grows large, it'll dominate this 3, and it'll also dominate this s squared term, except when s is large. And that'll become more clear later. But in essence, you can sort of imagine that our denominator becomes that sort of form. It's dominated by the kp terms as k becomes large. And if we factor that out, we can see that this approaches the form of the open loop numerator, which is also interesting. So looking at this, as kp becomes large, we get a pole at -2. And we also get a closed loop pole going out that way. So this picture that we've drawn by plotting each of the points shows all the possible closed loop pole locations for k varied from 0 to infinity. And if we kind of connect the dots, we can see those possible locations pretty clearly. So what we just drew there was in essence the root locus. It was the locus of all the roots, or the roots of the closed loop denominator. And the way that we did it was just by brute force. Go in steps of k, calculate new pole locations, plot them, calculate a new value, find a new value of k, calculate the pole locations, plot them, and so on. And if we were to ask a computer program like MATLAB to plot the root locus for us, that's what it would do. It would just do a brute force numerical plotting of points. It turns out, however, that we don't have to do it in that brute force manner. There's actually a procedure where we can draw this root locus based on the open loop transfer function. So it's interesting that we can determine all of the closed loop pole locations based on the open loop transfer function. And we're going to learn this procedure. What we will learn is just an approximate procedure to get a rough idea of the root locus. But if we want to get a more precise picture of the root locus, then we'll use something like MATLAB to do it for us. But it is beneficial to understand the basic idea so that we know how to modify the root locus with control. At this point, we're now going to try and explain where this drawing procedure comes from that we're going to learn. And this might be a little uncomfortable. You may not follow every piece of this explanation, and ultimately it's not necessary that you understand it completely. It's not something I'm going to ask you to do to derive the rules for drawing a root locus, but I'm just trying to, in a very hand-waving way, try to explain to you where these rules come from. And so the idea is that we can draw the location of all the possible closed loop poles for a given system, a negative feedback system, as we vary some parameter, which will normally be something like a proportional gain in our controller. And we're going to derive this procedure from the open loop transfer function. So for this system, go ahead and take a second and see if you can remember what we mean by open loop transfer function. Recall that the open loop transfer function is in essence, the loop. It's as if we took our negative feedback system, broke the feedback signal, and straightened it all out. So in this case, we have these forward dynamics G of S, and we have these feedback dynamics H of S, and the open loop transfer function is G times H, everything that's in the loop. So again, that might be a little confusing, but try and remember when we say open loop, it's as if we mean everything in the loop. Now let's think about what the closed loop transfer function looks like for this system. It's negative feedback, so it's simply forward over 1 plus loop, where the forward path from the reference to the output has only G in it, and the loop has G and H in it. So we get forward over 1 plus loop. That's our closed loop transfer function. Now let's think about where the closed loop poles come from. Closed loop poles are values of S that make the denominator of the closed loop transfer function equal to 0. So the closed loop poles can simply be found from this equation, where this is the closed loop denominator. However, it's interesting to note that this, the G times H, is the open loop denominator. So if we know what the open loop denominator is, we in essence know what the closed loop poles are without ever actually having to find the closed loop transfer function. And so what we're going to do is we're going to assume that we have some multiplicative parameter k that we'd like to examine how the system changes with changing of that parameter. Okay, so on the previous slide we had 1 plus G of S times H of S, and so in this case this is G of S times H of S, where we factored out a k. So this is the numerator of G times H, this is the denominator of G times H with a k pulled out. And if we rearrange this, subtract the 1 to the other side, divide through by k, we get that in essence the open loop transfer function must equal minus 1 over k. And this relationship is going to become the basis for the root locus procedure. Even if we had a situation where we wanted to examine how the system changes with a parameter that doesn't multiply the open loop transfer function, we could still rearrange the transfer function or this equation into this form. In that case, n and d aren't necessarily the numerator and denominator of the open loop transfer function, but we can still use this sort of procedure that we're going to generate. And so what this equation means is all of the points in the complex plane that are on a root locus must satisfy this equation for some value of k. Okay. Going back to this example of a root locus that we drew previously and recalling this relationship that we just derived, every value of S, which is a closed loop pole or a possible closed loop pole for our system, must satisfy this equation. So if we picked some value in our complex plane, some point in our complex plane, for example this point, and we plugged it in to this relationship, there would be no real valued k which would make this work. So there's no control gain k which places a closed loop pole at this location. However, if we picked any point that is on our root locus and we plugged it in for S, there would be a value of k for which these two are equal. And so that's what this says. looking at it from another point of view, if we plotted this point minus 1 over k in the complex plane, k varies from 0 to infinity, but this in essence is a real number, so it's on the real axis, and it's negative, so it's located over here. And we can think of this in terms of its radius and its angle, or in terms of its radius and its phase. So specifically, if we thought of this sort of in polar coordinates, the angle of that complex number is equal to minus 180 degrees, where 0 degrees is in the positive x direction. And so taking this relationship here, we can split it up into two conditions. One is the angle condition. Okay. So if we picked some value of s that's in the complex plane and we wanted to test it, this is going to be some complex number, in general. If we plugged in minus 2 plus 2j into our transfer function and expanded and reduced everything, this would be some complex number that has some phase and some magnitude. So in general, if this is a complex number that we get when we plug this in, it'll have some phase and it'll have some magnitude. In order for this to be satisfied, our phase needs to be minus 180 degrees. It needs to equal the phase of minus 1 over k. This angle is also the same thing as plus 180 degrees. It's also the same as 540 degrees. So in essence, adding multiples or subtracting multiples of 360 degrees brings us back to the same angle. So the phase for a given value of s needs to equal minus 180 degrees or minus 180 degrees plus some multiple of 360 degrees. So that's the angle condition, but then we also have the magnitude, where the magnitude is simply, you can think of it as the absolute value, but it's sort of like the hypotenuse, where the legs are the real part and the imaginary part. So we need to call this the magnitude condition. Okay. Where the magnitude of the left-hand side for some value of s needs to equal the magnitude of the right-hand side, where the magnitude of the right-hand side is just 1 over k. These two conditions form the basis of all of the rules that we will develop for drawing the root locus. Okay. Before we do that, though, let's take a look at the big picture. So recalling the magnitude condition, let's think about what happens as k goes to 0. So as k goes to 0, we have a finite number divided by something that's getting very small, so this blows up. So this gets very large. In order for this to get very large, either the numerator needs to get large or the denominator needs to approach 0. And so think about what values of s will make the denominator approach 0. Values of s that make a denominator 0 are the poles. So in essence, as k gets small, this blows up. In order for this to blow up, d must get small, and that corresponds to s approaching a value of the open loop poles, because d of s is the open loop denominator. So as k approaches 0, the root locus approaches the open loop poles. And this is something we saw in our previous example. Similarly, if k gets large, if k approaches infinity, then we have a finite number divided by a very large number, and this becomes 0. In order for the left-hand side to become 0, either d needs to become large or n needs to become small. And so values of s that make the numerator approach 0 or equal 0 are what? Zeros. So as k approaches infinity, this becomes small, this becomes small, this becomes small if n approaches 0, which corresponds to values of s that are equal to the open loop zeros. This too is something that we saw. Okay? And so this gives us sort of a big picture idea of what the root locus is doing. So stated in words, branches of the root locus start at open loop poles and end at open loop zeros. Note, if we have more poles than zeros, then this includes some zeros at infinity, which are called asymptotes. And that can be thought of as, so as k goes to infinity, n goes to 0, and the locus approaches open loop zeros. It could also correspond to the denominator going to infinity, and that corresponds to the locus approaching asymptotes. Okay? So going back to our previous example, so looking at this previous example, when k was 0, we started at open loop poles. So k equals 0, this was the location of the closed loop pole, which corresponded to the open loop pole. And as we made k approach infinity, one of our closed loop poles approached an open loop 0, and the other closed loop pole approached this asymptote. So in general, the rules for drawing the root locus, which derive from that angle condition and that magnitude condition, are the following. First, we locate open loop poles and zeros in the s-plane because they define where our locus starts and ends. We then determine the root locus on the real axis. We then determine the asymptotes of the root locus, that is, those zeros at infinity. In our case, we won't find the exact asymptotes. Rather, we're just going to approximate the asymptotes. We'll then find breakaway and break-in points, which again we won't find exactly, but we will just approximate. We won't determine the precise angles of departure and arrival, and we won't determine the precise location of where the root locus crosses the imaginary axis. So the rules that we're going to learn are just a sort of abbreviated way to draw a rough sketch of the root locus. If we want to understand in greater detail what the root locus looks like, then we'll use MATLAB. If you are interested to know for your own self what the procedure is for drawing a very precise root locus, you can refer to the book. And at this point, what these rules mean and what the precise terminology is might not make a lot of sense, but we will try and explain through the use of some examples. At this point, we'll now step through a quick example of how to draw the root locus by hand, or draw an approximate root locus by hand. This system is the one that we've already examined, where we, in essence, drew the root locus by brute force. And so in this case, I'm going to just quickly go through that root locus again in order to explain some of the terminology of the procedure, and then subsequently we'll do another example in a little more depth. So here's our approximate procedure. We want to draw the root locus, which is a graph of all the possible pole locations, closed loop pole locations, for values of k varied between 0 and infinity. And so the very first step is to locate the open loop poles and zeros in the S-plane. If you recall, the open loop pole, we had conjugate poles, one at -1 plus root 2j and -1 minus root 2j. And we had an open loop 0 of -2. And so this defines where the branches of our root locus begin. They begin at open loop poles and they end at open loop zeros. So that's step 1. Step 2 is to determine the root locus on the real axis. So if we look at the real axis, it's split up into kind of two regions. There's the part of the axis that's to the right of our 0, and there's the part of the axis that's to the left of our 0. It turns out that our root locus is only located to the left of the 0. And I'll explain subsequently how to determine that. So if you were to sub in points on the real axis over here into our angle condition or our magnitude condition, they wouldn't satisfy those relationships. However, if you picked a point over here, such as -3, it turns out there would be a value of k between 0 and infinity that satisfies the angle condition and the magnitude condition. Step 3 is to approximate the asymptotes of the root locus. And so if you recall, all branches start at open loop poles and end at open loop zeros. So one of our branches will start at an open loop pole and end at an open loop 0. However, we have more open loop poles than open loop zeros. So one of the branches starting at an open loop pole is going to go to a 0 at infinity, which is also called an asymptote. And it turns out, or if you recall, we have an asymptote that goes to the left along the real axis. So that's our asymptote. So as k becomes large, one of our poles is going to move out in that direction. Step 4 is to approximate breakaway and break-in points. So in this case, we have one branch starting at that open loop pole. We have another branch starting at that open loop pole. One of the branches is going to go to this asymptote. The other branch is going to go to the open loop 0. Okay. Where these arrows define how the poles move as we increase k. So here we're starting at k equals 0. As we increase k, the closed loop poles move, and as k approaches infinity, they move like this. This point where these two branches meet and then spread out along the real axis is called the break-in point. This break-in point defines where the two branches come together on the real axis. Breakaway points, consequently, are where two branches come together and break away from the real axis. Technically, you can have breakaway and break-in points that aren't on the real axis, but for the vast majority of cases they will be on the real axis. Step 5, which we won't do in this class, is to find the angles of arrival and departure. So this angle defining how the branch departs that open loop hole is called an angle of departure. Likewise, this is an angle of departure. So based on our rough approximation, we don't actually know that the root locus would go that direction. Technically, it could go flat or it could go underneath, but for our purposes, we're okay with not knowing precisely what the angle of departure is or the angle of arrival. Step 6 of the procedure, which we also won't do when we draw the locus by hand, is to find where the root locus crosses the imaginary axis. So in this case, there are no imaginary axis crossing. The root locus stays entirely in the left half of the complex plane. And what that means is that this closed loop system will be stable for all values of k. There are other systems that we'll see, however, that there are values of k for which the locus will move into the right-hand plane, where the real part of the closed loop poles are positive, which indicates that the system is unstable for those values of k. So at this point, we're going to go ahead and do a more detailed example where we get a little bit more specific about how to draw the different aspects of the root locus. So recall, the very first step is to locate the open loop poles and zeros. Looking at this negative feedback system, recall that the open loop transfer function is the loop transfer function. So it's everything in this loop. It's as if we took this feedback path, broke it away from the summing junction, and straightened it out. So the open loop transfer function is a gain times the quantity s plus 4 divided by the quantity s plus 1 times the quantity s squared plus 2s plus 2. And so just by inspection, we can very easily see that we have one open loop 0. It's equal to negative 4. And then we can also see that we have 3 open loop poles because we have a third order denominator. One of the poles is easy to see. The pole due to this term is just negative 1. And then the poles due to this term are complex conjugate, and they can be found by applying the quadratic formula. Turns out that they're equal to negative 1 plus minus j. So these are our open loop zeros and our open loop poles. Once we've found those, we can go ahead and plot them. So we have an open loop pole at minus 1, have an open loop pole at minus 1 plus j, and an open loop pole at minus 1 minus j. And I'm indicating the open loop poles with these x's. We also have an open loop 0 at negative 4, where I'm indicating the open loop 0 with an O. These locations are important because we know that our root locus begins at open loop poles and approaches open loop zeros. So starting at k equals 0 and approaching k equals infinity. Step 2 of our procedure is to determine the root locus on the real axis. Okay. And this derives from the angle condition. So looking at this, I'll real quickly draw in our poles and our 0. Okay. What we can do basically is we can break the real axis up into 3 distinct regions. We have the region to the left of the 0, we have the region between the 0 and the pole, and we have the region to the right of the pole. And so we want to test each of these 3 regions by picking a point in each of those 3 regions and testing whether or not they satisfy the angle condition. Because we know that any value of s that's on our root locus, that is a closed loop pole location for some value of k between 0 and infinity, must satisfy both the angle condition and the magnitude condition. So for region A, we know that the angle of this complex number when we pick some value of s and we plug it in to the open loop transfer function, it must equal minus 180 or some multiple of minus 180. And furthermore, if you think back to the very beginning of the class, if you looked at that review material about complex numbers, you may recall that when we're dividing two complex numbers, their angles subtract. So you can imagine them in sort of an exponential form or Euler form, where the angle of the numerator subtracts the angle of the denominator complex number. And so another way to think of this is these are angles from zeros, and these are angles from poles. So if we pick a test point out here in the A region and we draw an angle from the 0, you can see that the line drawn from the 0 to a test point in the region A is minus 180 degrees or positive 180 degrees. It's in that direction. So that's our only 0. Then we subtract angles from poles. And so in this case, if we draw a vector from this pole to our test point in the region A, it's also at an angle of 180 degrees because it's pointed that direction. We also have angles from these two poles. So you could imagine if we drew a vector to that test point, have some angle theta 1, and if we drew some vector from that open loop pole to that test point, we have some angle we can call theta 2. You'll notice that this theta 1 and this theta 2 sum to 360 degrees. Okay. And since adding 360 degrees to an angle basically takes us back to the same angle, to the same location, we can disregard these conjugate poles that are off of the real axis, because they will always, their angles will always sum to 360. In essence, they always cancel. So we don't have to explicitly take them into account. So looking at the rest, we have 180 degrees subtracting 180 degrees plus, some multiple of 360. That sums to 0 or 360 or 720 or whatever. And think about, does this satisfy our angle condition? It does not, because what we need is we need for the angle to equal minus 180 degrees plus or minus some multiple of 360. 0 is not equal to minus 180 plus or minus some multiple of 360. So that means our root locus is not located in the region A. If we pick a test point here and sub it into our open loop transfer function, it will not satisfy the angle condition and the magnitude condition. It will not equal minus 1 over k for some value of k between 0 and infinity. We can then go ahead and test region B, where again we draw the angles from the numerator from the zeros and subtract angles from the poles. In this case, if we draw a vector from the 0 to the test point in region B, that's at an angle of 0. And then if we draw an angle from the open loop pole at minus 1, that's to the left, so that's an angle of 180 degrees. We don't have to explicitly consider these conjugate poles because we know that their angles will always sum to 360. So 0 minus 180 is equal to minus 180 degrees. Thinking back to our angle condition, that does satisfy our angle condition. We needed it to equal minus 180 plus or minus some multiple of 360. So this will be part of our root locus, the region B. We then test a point in region C. Same condition. Look at the angles from zeros and subtract the angles from poles. So if we draw a vector from that 0 to a test point in region C, that's in that direction, which is equal to 0 degrees. If we draw a vector from the open loop pole, it's in the same direction, so it's also 0 degrees. 0 minus 0 is 0, which does not satisfy the angle condition, where we need to equal negative 180 plus or minus a multiple of 360. So going back to our previous slide, we have that our root locus includes this portion of the real axis. So there are values of k for which we can place closed loop poles in this region. So we can have closed loop poles that are real valued in between -1 and -4. But we can't have real valued poles that are greater than -4, and we can't have real valued poles that are less than -1 or greater than -1. Thinking back to the fact that branches start at open loop poles and end at open loop zeros, this is going to be one of our branches, where when k equals 0, the pole is located at -1, and as k gets larger, this closed loop pole will move from -1 to -4. We will then also have branches coming off of these open loop poles. So this procedure of applying the angle condition to test where on the real axis the root locus is located is a little tedious. You may have been able to recognize a pattern, and it turns out that in general branches lie to the left of an odd number of poles and zeros. So again, we don't have to consider poles and zeros that are off the real axis because they come in conjugate pairs and they cancel. So all we have to do is look at the poles and zeros on the real axis. Region A is to the left of 2 elements, 1 pole and 1 zero. So since region A is to the left of 2, 2 is an even number, we have no locus in this region. If we look at region B, elements in region B are to the left of 1 pole, are to the left of 1 element. 1 is an odd number, so we do have a root locus in this region. And region C is to the left of no poles or zeros, so it's to the left of 0 elements, and 0 is an even number, so again we have no root locus in this region. And so this is a nice little shortcut if you don't want to go through applying the angle condition for every region. Step number 3 is to approximate asymptotes. If you recall, the number of asymptotes is in essence the number of zeros in infinity. So if we have 5 open loop poles and 2 open loop zeros, that means we have 3 more open loop poles than we do open loop zeros. And so those branches are going to go to zeros at infinity, i.e. our asymptotes. And so what we're going to do is we're going to just memorize the directions of these asymptotes for some basic cases. When we have 1 zero at infinity, this was the first example we saw where we had 2 poles and 1 zero, so 2 minus 1 gave us 1 asymptote. that asymptote went off to the left at minus 180 degrees, or positive 180 degrees. So when we have one asymptote, 1, 0 at infinity, it'll always go to the left along the real axis. When we have 2 zeros at infinity, we'll have one asymptote going to plus 90 degrees and one asymptote going to negative 90 degrees. So we'll have something like this. When we have 3 zeros at infinity, we're going to continue this pattern of symmetry. So we'll have one at 60, 180, and 300 degrees. So I have one going up at 60, one going to 180, and one going to 300. When we have 4, then we similarly split up the 360 degree pie into four slices. So each of these, when we had 3, are 120 degrees apart. When we have 4, they're each 90 degrees apart. So we have one at 45, 135, 225, and 315. This pattern continues. So if we had 5, they split up the 360 degrees into five symmetric directions. Looking at this, we can memorize the directions of the asymptotes for each of these cases, and these will always be the directions of the asymptotes. What we won't solve for by hand, however, is the exact location of the asymptotes. So we'll know their directions but not their locations. We won't know where the asymptotes intersect the real axis. So technically we won't know if the asymptotes intersect in the left half plane, or if they intersect in the right half plane, or if these are centered, at -1, or if they're centered at +5. That we won't know. There is a way to calculate that. You can find it in your book, but for our purposes we're happy to just get a rough sketch of the root locus. Looking at the example that we started earlier, we have 1, 0, 1 open loop 0, and 3 open loop poles. So since we have 3 poles and 1, 0, we're going to have 2 asymptotes. We're going to have 2 zeros at infinity, and they'll go off at +90 and -90. So if we go back to our picture, we can go ahead and draw that in. So we know that our asymptotes will go at +90 and -90, but we don't know if the asymptotes will be located over here or over here. It turns out they're in the right half plane. So you'll have some asymptote going up at 90 degrees, and you'll have some asymptote going down at 90 degrees. And you'll end up with something like this. Okay. As you get a little bit more practice, you will start to sort of get a feel for what direction the branches are going to head in. If we want to know the precise location, we can go ahead and use MATLAB to draw the root locus. Continuing on with our procedure, step 4 is where we approximate breakaway and break-in points. This locus does not have any. In general, breakaway and break-in points occur when branches come together. In this case, we have no branches that come together. If you recall, we have a branch going that way, a branch going that way, and a branch going that way. So they never meet. In general, a good sort of thing to look for is that breakaway points They tend to come between poles on the real axis, and break-in points tend to come between zeros on the real axis. Since we know that branches leave poles, you can sort of imagine two branches leaving two poles and meeting in the middle and breaking out. And since branches approach zeros, you can also imagine two branches meeting on the real axis and then breaking in to approach the zeros on the real axis. That might not be very clear. You can look at the first example we did to see an example of a break-in point between the 0 at -2 and the 0 at infinity. And in a minute we'll do another example that'll give another picture of what this situation means. Step 5 uses the angle condition to determine angles of departure and angles of arrival. So in this case we have these angles of departure. And step 6 is used to determine where the locus crosses the imaginary axis, and it uses the magnitude condition. And so again, we'll skip that when we draw things by hand, but it is important. So for example, in this root locus you can see that if you increase k enough, the closed loop poles will move from the left half plane into the right half plane. So this is a conditionally stable system. There are values of k for which we will place the closed loop poles in the right half plane and the system will be unstable. In order for us to examine these properties, we will use MATLAB. Okay. At this point we'll go ahead and do another example. Recall step 1, locate the open loop poles and zeros. Okay. So this is the open loop transfer function. It has this constant k that we want to find how the closed loop poles vary with that k. The first step, we're told, is to locate open loop poles and zeros in the S-plane. Okay. So by inspection we can see that we have a 0 at -3. By inspection we can see that we have 4 poles, one at 0, one at -1, one at -2, and one at -4. Step 2 is to find where on the real axis the root locus is located. And so one approach is to apply the angle condition repeatedly to different regions of the real axis. The second approach is to look and see where on the real axis are we to the left of an odd number of poles and zeros. Okay, so we're looking for where the sum of the number of poles and zeros is odd. Step 3 is to locate asymptotes. So go ahead and look at our transfer function and think to yourself, will we have any asymptotes? How many asymptotes will we have? Okay, since we have 4 poles and 1 zero, we will have 4 minus 1. So 4 poles minus 1 zero equals 3 zeros at infinity. And we will memorize that this corresponds to directions of 60 degrees, 180 degrees, and 300 degrees, though we won't know exactly where these asymptotes intersect. Step 4 is to look for breakaway and break-in points. And it turns out, as I mentioned previously, that we will have breakaway points at locations between poles on the real axis. So you can sort of imagine this. So here's our real axis. We've got 0, -1 pole, -2 pole, got a 0 at -3, and then another pole at -4. So let's go ahead and skip back up to step 2 for a second. So the root locus will be located to the left of an odd number. So out here, we're to the left of no elements, 0 elements. 0 is an even number, so this part of the real axis is not on the root locus. In this region, we're to the left of 1 element, 1 pole, and since 1 is odd, we will have a root locus here. Here we're to the left of 2, 2 is even, no root locus. Here we're to the left of 3, 3 is odd, so we have root locus. And here we're to the left of 5. 1, 2, 3, 4, 5. 5 is odd, so we're to the left of the pole at -4. Looking at this, our branches start at open loop poles and go to open loop zeros. So that's a branch. As k increases, a closed loop pole will move from -2 towards -3. Here we have another branch that starts at -4, and it's going to go to a 0 at infinity at an asymptote, where one of our asymptotes goes to -180. Here we have 2 more poles where branches leave those poles. So you can imagine we have one branch leaving that pole at -1, one branch leaving that pole at 0, and at some point they're going to hit each other. They're going to bump into each other in between 0 and -1, and they're going to break out. So we have a breakout between 0 and -1. In general, when you have just 2 branches coming together like that, they will break out or break in at 90 degrees at right angles to one another. And these, once they break out, will then approach these 2 asymptotes. So the branch that started at -4 approached the asymptote at 180. The branch going up is going to approach the asymptote at 60 degrees. The branch going down will approach the asymptote at 300 degrees. And you'll get something that looks like that. I'll go ahead and redraw that a little bit better on the next slide. So step 1, locate poles and zeros. Pole, 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 0 at -3, and then another pole at -4. We locate the root locus on the real axis for step number 2. This is to the left of an odd, this is to the left of an odd, this is to the left of an odd. Step number 3 is to find the asymptotes. We have 4 poles, 1 0, so that means we must have 3 asymptotes. So that branch starts at that pole and goes to that 0. This branch needs to go to an asymptote at 180 degrees. These 2 are going to go, one to an asymptote at 60, one to an asymptote at 300. And between these 2 poles, we will have a breakout point. The branch leaves that pole, the branch leaves that pole, they bump into each other, they break out at 90 degrees, and they approach the asymptotes. So in general, we will know between which 2 poles we have a breakout, or between which 2 zeros we have a break-in, but we won't necessarily know the exact location. So it's not necessarily the case that the breakout point is at 0.5. The breakout point isn't necessarily halfway between the two poles. Again, there's an equation for calculating that location in the book, but for us it's just good enough to know between which two poles and which two zeros we have breakout and break-in points. Similarly, we won't calculate where this cross is, though we could determine it using MATLAB. In this case, all of our angles of departure and all of our angles of arrival are determined. So these are angles of departure where we leave poles. Here we have an angle of arrival where we approach a zero. And this is a rough sketch of a root locus. It's not exact, but we can tell quite a bit from it, and we were able to draw it relatively quickly. Always remember to put arrows indicating the directions that the poles are moving, where we start at small values of k approaching 0, and we move in the direction of increasing k. All the closed loop. This brings us to the conclusion of Module 17. In this module, we learned about the Root Locus tool, which is a graphical tool for visualizing all the possible closed-loop pole locations for a given parameter change, for example, a proportional gain k. We learned how to draw this root locus based on angle and magnitude conditions from the open-loop transfer function. So this is quite interesting that we can draw this root locus, this picture of all the possible closed-loop pole locations without ever actually finding the closed-loop transfer function. We draw it straight from the open-loop transfer function. And while we learned what the angle and magnitude condition were, that's really not what's most important for us. What's most important is this procedure that we learned in order to draw a very approximate picture of the root locus. If we want to draw a more exact picture, then we use some sort of software tool like MATLAB.